Hi everyone. This is a lecture for Kin 376, the undergrad biomechanics course. Um, this is going to be the third to last lecture for this class. Today, or for this lecture, we're going to be talking a little bit about movement variability. This lecture is going to be kind of short, and it is important to understand the basic principles of movement variability, and we'll go over those and we'll review them for the final exam review, because this will play not a large part, but kind of a smaller part on the final exam. So we won't really get into excruciating detail when we start talking about variability, but we'll kind of cover the broad strokes and understanding the basis of what we're talking about, that when we look at movement, it's not always consistent, and this could lead to positive or negative outcomes. There's possibly reasons that variability may be different from person to person, and stuff like that. If you can understand the basics of that stuff, you should be fine. So let's get started. So when we start talking about variability, we have to kind of look at what is the goal of biological functioning. We're all humans, or at least I hope we're all humans here. But the ultimate goal for biological functioning is to reach homeostasis. This is considered a stable state. So when we talk about homeostasis, if you've taken, intro to biology, this is one of the first things that's kind of taught, especially when we look at, biology as a changing system, which is kind of funny to me. They say the point of a biological system is to reach homeostasis, but if we're looking at biology changes constantly. That's what evolution is. So kind of saying, well, the point of a biological system is to reach homeostasis, but all biology evolves over time and changes over time, seems kind of opposite to me. So when they say it reaches homeostasis, the kind of point is it should be at optimal functioning across time, I guess you could say, is reaching homeostasis, but a lot of times they'll say it reaches a stable state. And this is true for our basic involuntary systems. When we look at red and white blood cell count, our heart rate, they usually say, the optimal heart rate or kind of normal functioning heart rate is 60 beats per minute. Usually for everybody, we like to say a healthy heart rate is usually somewhere in between 60 to maybe 85 beats per minute. Obviously, if we're looking at, endurance athletes, long distance runners, if you're looking at, endurance athletes like Lance Armstrong, he had a resting heart rate of like 30 beats per minute. His heart would beat every 2 seconds. And that's simply due to training his heart and body was able to make better use of oxygen in the blood, so it didn't need to pump as much. Blood pressure, we'd like to say that optimal blood pressure, good blood pressure, is equal to or less than 128 or 120 over 80. Anything above that, we start looking at hypertension. Usually, if we're looking at very low blood pressure, something like 60 over 80 or 80 over 80, we might say that's hypotension. But usually we like to say everybody should hover around close to 120 over 80. When we look at basic voluntary systems, so especially when we're looking at gait or other movement patterns, running, walking gait, riding a bicycle, swimming, do we really want to see that, our gait is stable? Of course, we want to see our gait and balance are stable so that we don't fall, but when we look at kind of the details of the gait, from we'll talk about it a little bit later in this lecture, but when we're looking at heel strike to heel strike, which is one gait cycle, if we look at many of these, is every gait cycle the same time? When we look at the kinematics of the foot ankle, do we see exactly the same amount of angular displacement? If we did, would that look more normal or less normal? When we're going to look at kind of robots functioning is when we build robots that can walk is, yes, their angular displacement is exactly the same each time. But when we look at that, there's kind of a saying, it looks beyond the pale. This is kind of, it's a philosophical kind of statement. They use it for, it's kind of a little bit of the same statement when they're making CGI movies and even CGI movies, or they're using graphics in video games. Is they're making, in the CGI movies, they make figures that are almost perfectly symmetrical, and they try to do motion captures so that they can make them move normally. But if they don't take a big enough sample, it almost looks like the people moving on the movie screen or on a video game are almost robotic. And so it's kind of beyond the pale. It doesn't quite make sense to us. That's why when you're watching a lot of the bigger budget Hollywood blockbusters, is they do try to go through great lengths to make it look realistic. But there's still a lot of times you look at it and you're kind of like, especially if you're looking at any sort of action or fast-paced stuff, that's why they do a lot of cuts to make, especially in the CGI fighting, like if you watch the Avenger movies, there's a lot of cuts in that because they're CGI heavy, and they don't necessarily want you to look at the animation for too long. If you were to look at it for a little bit longer, all of a sudden it starts looking a little bit unreal because it's very, very hard to get the kind of, as good as people have gotten with it, it's very hard to look at kind of the slight changes that you are normally see in real life examples. And one may expect a constant output unless responding to a stimulus. That's where we kind of look at our homeostasis, is that our heart rate shouldn't change unless there's a stimulus. Our breathing rate shouldn't change unless there's a stimulus. Your gait from your stride time and length should be about the same unless you're changing it. But is this really the case? Even without what we can see as our perceivable changes, as far as what we can notice, is this output constant? So here we have 3 examples. Does this look like homeostasis? Does this look like a body's resting without any sort of external input? Nothing's really changed, but we can see in our white blood cell count over 800 days, it's constantly changing. Same thing with our heart rate over time. Our heart rate this is taken from somebody we consider them to be, a healthy, normal functioning person, but even their heart rate is changing little bits over time. Even our blood pressure, we can see, is almost like a sine wave, okay? Last time we almost can identify weird sine waves, but are these sine waves even consistent? A normal sine wave is like this, but, that would be a non-variable sine wave. It would be a consistent sine wave, but a lot of times we'll see it'll kind of be like this and spread out, and then it'll bunch up again. So when we look at biological systems, we don't really see that it's perfectly consistent. And that's one of the big reasons for that is, our body is, we have our nervous system, we have our cardiac system, we have the skeletal muscle system, we have the endocrine system, we have, your blood sugar and the hormones that are produced, that's our endocrine system. You have all these separate systems, and each one of these separate systems is composed of a few different organs. It has different thresholds for input. So there's a lot of factors in here, and to kind of expect them to all work in perfect harmony all the time and know exactly what the other one needs at any given moment is kind of a big ask. So wouldn't it be simpler to say that a lot of times when we look at these biological systems, yes, they are working in concert with each other, but a lot of times they may be operating a little bit autonomous from each other. So that's why we might see a considerable amount of variability between these systems. And is that a good thing or a bad thing? That's kind of what we'll touch on today. We can look at the voluntary biological systems as well. This is our gait. This is our stride time over time, okay? So how did our stride time change over 5 minutes of, say, walking on a treadmill? We see that maybe there's a little bit of this sine wave in here as well, but even if I just kind of draw over it, is it really that sine wave? Does it look consistent? Why might the stride change? Even if we're walking on a perfectly flat treadmill, why does that stride change seem so inconsistent? Even with finger tapping, okay? We're just tapping our finger on the table like this. That sounds nice and consistent, almost like a metronome. But if we're just kind of left and we maybe do it for longer, do we see slight changes in displacement? Does it go up and go down without really any sort of reason? And once again, that's due to simply I'm tapping my finger, but maybe each time I tap my finger, the impulse sent to my finger flexors and extenders is a little bit different. Do I just have no rhythm whatsoever? People have said that when they see me dance, so that's possible as well. But could it be simply my heart was beating, possibly at a different rate than my finger was tapping? So my nervous system decided I want those to be in sync. So one of them has to speed up or slow down. They overshoot each other. All of these variables have to be calculated all the time. So it's a little weird for us to say that everything is going to be consistent all the time. And once again, if we look at everything being perfectly consistent, especially if we're looking at humans, does that seem human-like? If you're looking at somebody and they have the exact response each time, they're almost walking robotically. If you were to observe that, and you're observing that with your eyes, you're kind of like, something is a little bit different. So why? Why shouldn't there be a normal level output regardless of that system? Before we even answer that question, let's look at what a system has to deal with to function, to keep you upright, to make sure enough blood gets to your lungs or to and from your lungs, to your muscles, to make sure your heart's getting enough oxygen, to make sure your brain's getting enough oxygen and glucose. What are the determinants of that system that it needs to function? Heart rate. What causes a heart to work harder or lighter? Obviously, the easy one is the harder you exercise if you're running, the faster you run, the longer you run, it needs to start working faster and harder. But what about stress? Does stress, when you're taking the final exam, is your heart rate going to go up a little bit? I hope that, it's not too easy, but I hope it doesn't cause a panic attack and you get all flustered and like that, but your heart rate's probably going to change a bit. So our resting heart rate is around 60 beats per minute. Like I said, it's going to, depending on what you're really looking at, it can be usually anywhere between 60 and 85. But we see that it changes constantly with our exercise, exertion, when we're resting. If you're one of those people that gets really bad hiccups, you're going to notice a change in your heart rate all the time. So it changes. There's lots of external factors. So how often do we ask our hearts to just rest? Okay. What does that even mean? So in the last minute or so that I've been talking, did you move in your chair? Did you kind of squirm around a bit? Probably drifting away a bit, or you just kind of squirming, rolling your eyes, stuff like that. Did you change your breathing patterns? Usually when we look at breathing, just like heart rate, it's never quite consistent. Same thing we see is under stress. People change their breathing pattern. Some people, when they experience high levels of stress, they begin to hyperventilate. Did you move your feet or toes a bit? Are you kind of tapping your toe while I'm talking because you're starting to get a little bit bored? You're like, when is he going to stop talking? All of this stuff is basically, are you awake? Are you a living system? Okay? Are you a biological system that constantly changes just a little bit? If you answered yes to any of these questions, you asked your heart rate to adapt, to stop resting. So when we look at this, maybe the heart rate by itself, even without any sort of stimulus, is constantly changing just a little bit. And then when you do stuff that needs a greater or lesser heart rate, the heart itself is already at possibly an optimal heartbeat for that. So if you answered S, you're simply asking your heart to adapt, stop resting. Okay? If it's always consistent, and then all of a sudden you shock it saying, now you have to do this, it's harder for it to get moving. When we're looking at impulse in our kinetics, and we found, if we're trying to get something to move against friction, we found that it's harder to get it started than to keep it going. So if it's so much harder to overcome inertia and friction than to keep something moving, well, why not keep it moving all the time? Have it constantly changing. So if our heart rate is consistent, we'd have simply something like this. Nice flat line at 60 beats per minute across all times. Does that look like a good, healthy heart rate? Okay, it's locked into a set response and allows no flexibility or adaptability. When we start talking about this, and this really won't be kind of a big thing on any of the exams, but it's kind of a good way to look at this is if you've ever heard of the term game theory. Game theory is it's like a philosophical and statistical ethos, really. That the big example is if you're on a game show and you're told that there is a car behind 3 different doors, and you pick, let's say, the first door, and there's nothing there, but there's a car behind 3 doors and nothing besides the second door. You say that it's going to be behind the middle door. Before your answer is revealed, the game show host may open the first door and there's nothing there. He then asks, do you want to change your guess between maybe the middle and the last door? What game theory suggests is you should. Even if you're really, really certain that it was behind the middle door, you should change your guess because now you went from a third of a chance of being right to a half a chance. Your chances have increased. Okay? You won't really need to know about that, but what we're basically saying is as things adapt and change, the chances of them being correct also change. So we see that with increased flexibility and adaptability, that we're starting to see that at any given moment when that change is needed, it will be available. This is kind of a little bit like game theory. I won't ask you questions about game theory, but it's really kind of interesting to look at. There's plenty of really cool books on it, articles on this stuff. You can go on YouTube and type in game theory explained. There's going to be tons of really cool lectures and videos that kind of go in depth of it. And it's kind of a cool kind of philosophy to kind of think about and know. And who knows, you might impress somebody one day at a bar or a party and they'll think, oh boy, this person's really smart. So normal healthy functioning looks like this, okay? It's not that straight line. Even I can't even draw a straight line. My straight line is variable, okay? It's changing a little bit. But this is what we look at when we look at a normal heart rate. It's changing just a little bit. It must have some variability built into it to adapt to what we consider perturbations or perturbations. Okay, perturbations is small little effects. Okay, what we see in balancing is when we talk about balances, you're never really standing perfectly still. You have a little bit of sway to it. That sway is the result of small little perturbations, either due to wind resistance, you just kind of normally shifting. So we start seeing adaptability and variability so we can adapt to those perturbations. So gait. Let's talk about gait. Obviously, we've kind of got into this as gait is not perfectly stable all the time. It's not like these little animations right here. In human function, gait, our stride length, our stride frequency, how we land on our foot, even if we take all these into consideration, our normal speed changes all the time. Walking is a fundamental motor task and is performed in nearly every human. In the simplest of situations, do we get this constant gait behavior? Can we walk like robots? Well, if we put our minds to it, maybe. But you can even look at some of the greatest musicians there are, especially some of the more famous drummers. Okay? When you look at some of the very famous drummers, they're known they can keep a beat really well. But if you really listen to that music, even when they had a really good producer and a really good studio that laid in a lot of tracks and they did a lot of takes of the same song, if you really listen to it, you'll notice that even that beat changes just a bit every minute or so. It's constantly changing just a little bit. If you wanted a very, very consistent drummer, you could simply get a drum machine. They did that in the 80s. They do that today with, even we look at auto tune when people are singing, is we're simply using it to make sure that we don't see any real changes in pitch. There's no variability to that. So yes, we can do that. We could try to walk like robots, but for how long before it becomes almost too hard to keep that consistent and our natural variability takes over. So gait. First, how can we measure whether a gait is consistent or not? This right here is considered to be one gait cycle. One gait cycle, kind of mentioned this already, is if we consider this to be the right foot here, is the heel strike of one leg to the heel strike of the second leg. So it's heel strike to heel strike. This is where we look at the gait cycle. Heel contact to heel contact, or heel contact or heel strike to heel strike of the same foot. So right now we're just looking at the blue leg. This is our stride to stride interval or one gait cycle. You'll hear those two terms looking at. What we do is we'll measure the time of each stride to stride interval and see, is that the exact time each time? We might also measure the timing of steps between similar steps is similar to measuring the time between heartbeats. We might use foot sensors instead. When these foot sensors here are forced down on the ground on the heel and forefoot, it simply sends a signal up to this wire and basically ticks. Okay, it allows for a very precise way to capture when each heel strike occurs. So let's look at this. As the person's walking, the force sensor is triggered, and we see this little spike right here. This is our force. Okay, and then as we move from our heel to our forefoot, this force starts to decrease. It starts sloping downwards. So this we have our force characteristics, or force kinematics or kinetics, over 10 seconds of somebody walking. So we have heel strike to heel strike, heel strike to heel strike to heel strike to heel strike. So we've measured 1, 2, 3, 4 stride to stride intervals. Okay, we are measuring a different color. We are measuring this interval here, here, and here. And we're just trying to see is how variable or how consistent these are. So we determine the time between each heel contact, just like we might look at in heart rate. When you're looking at an ECG, you'll often hear them referred to EKGs. EKGs only work in Germany because German doesn't use the C, they only have K. In the US, we say ECG, it stands for electrocardiogram. We spell cardiac with the C, we don't spell it with a K. But you'll see an electrocardiogram signal look something like this. Not perfect, but it'll look something like that. We measure, I'll draw that again, but it looks something like this, like a strip on an ECG will look something like this. Okay, it's not perfect, but we measure this interval. We call it the R to R interval. That's the time between each beat of the heart. We can look at something similar when we're looking at the time between each heel strike. So we have 1, 2, 3, 4, 5. These are our 5 different heel strikes. So in this example, the stride to stride interval is, we're seeing it's between, this is the first one here, this is the second one here. The first one occurred at roughly 2.4 seconds. The second one is 3.5 seconds. And this is similar to how we measure displacement. It's always, for displacement, it's position, but we're looking at time. So it's time, that's not how you write a T. We're looking at time 2 minus time 1 is going to be our change in time. So 3.5 minus 2.4 gives us 1.1 seconds. So one stride took approximately 1.1 seconds. Normally, if we're looking at gait analysis, this process is repeated for every stride. So roughly we get 800 strides in 15 minutes of walking. And we look at the stride to stride interval of all 800 of those. And that's where we start looking at, well, what was the standard deviation between these two? What was the standard error? If you've already taken Kinesiology 370, hopefully those terms are not too alien to you, but we're looking at variability measurements between these strides. And there's some other very, very fascinating statistical methods and models to do this, but you don't need to know those. They're really fun to do, but it's hard to do them by hand. We use MATLAB. If you know what MATLAB is, awesome for you. It's a programming language that we build statistical models on. It's a whole lot of typing very weird symbols onto a computer screen. But generally, we start looking at how variable is these stride-to-stride intervals. So the intervals for each stride are compiled, and we call that a time series. And the plots show the stride interval time series for 800 strides. So right here, this is our 15 minutes of treadmill walking at a self-selected speed. And we use the same tools to study gait and heart rate and other biological systems. But then we kind of calculate, we kind of clean it up and we build a model so we can see this stuff. And we see that it's constantly changing. Same thing with our stride to stride interval here. It's not, it's not a perfect, consistent thing. It's kind of changing all the time, all right? Even if we're trying to find, like, there's a signal, we call them signals, that's kind of, consistent. There's no, get a different color here, but there's no real, if I just kind of draw through the median of everything, there's no real rhythm to be seen here. We can see smaller rhythms, kind of self-alike rhythms within this whole graph, but as a whole, it's always changing just a little bit. So why don't we walk like a robot? Obviously, hopefully you understand that obviously we don't. But why don't we? The environments we walk in all the time are complex and require adaptive locomotion. When we were still on campus, when you had to cross, Spring Street, that's not the correct word. I already forgot the name of the major road on campus because I've been away for so long. Or you're crossing over Walker Avenue or anything like that, or Spring Garden Street, thank you. Can't believe I forgot that. Is not only do you have to adapt to the height of the curb, any changes in the concrete itself, concrete's never perfectly flat. If you've ever been to Michigan, where I'm from, you know that very well. We have some of the worst roads, and I think we actually do have the worst roads in the country. We over-salt our roads and have really large semi-trucks drive on every road, and they The freeze and thaw basically breaks up all the concrete, so we get big holes in our roads. But the concrete is never flat, so you have to adjust to elevation changes. You have to go up curbs. You have to dodge cars. All this stuff, it's very complex. If you are walking very consistently, you wouldn't be able to adapt to the changing environment around you and be bumping into things and tripping. If you ever walked on a crowded street or sidewalk and you've got different people walking around you, they're all walking at different speeds. Some people, which I despise, will walk shoulder to shoulder, at a very nice slow pace, and take up the entire sidewalk, and you have to kind of do a little shimmy around them to get through them, so you can make it to your building at a reasonable time. Okay, so you've got to kind of move around obstacles constantly. If you're walking like a robot, that would simply make it harder. So walking like a robot would increase our chances of failing and sustaining an injury. It makes it harder for us to overcome this complex kind of environment. Good example of that is the Honda Motors Asimov robot. It's not the world's most advanced humanoid robot anymore. It used to be. This thing was designed in the early 90s, and it was amazing to watch. Here we can see it's walking by itself. It's programmed to do this. Nobody controlling it. But look how it's walking. It's walking very consistently. And now all of a sudden it has to go upstairs. You can see right here, it stops. It's got to stop and assess these stairs. Okay, I'm going to pause it just a little bit if I can. I can't. But it's got to stop to calculate all this stuff because it's walking very consistently. It's got to look at all this stuff. And so now it's calculating, okay, well, how wide are the stairs? How tall are the stairs? How many are there? Like that. It's looking at the audience saying, I don't even have to look at this because I've got it programmed into me. Now, it just made a mistake and it falls down. Okay? It didn't have the computing power to quite understand how to do it. And also, it can do some dancing. It doesn't dance very well, but you'll find videos of it dancing with little kids. It's incredibly cute. But this is where they were first showing it. All of a sudden it fell, and Honda was very embarrassed. They quickly brought out some blinders and said, okay, show's over. You didn't see that ever again or anything like that. So that's how robots walk. It doesn't look as efficient as humans. And you wouldn't really want it carrying your coffee for you. So if movement variability is advantageous, why do we train our athletes or patients? Why do we train them to be overly consistent? That is, why do we not teach variability when we're going through rehabilitation, or if we're teaching pitchers to pitch? Why don't we teach them variability? The simple, short answer to all of this is especially us biomechanics, we don't understand this problem well enough yet. First, we have to develop a considerably good model for this. Then we have to figure out, well, how do we coach this? How do we teach this? Can we build machines that can do this? This treadmill right here uses programming and variability that it constantly changes the speed of the treadmill. It brakes, it stops all of a sudden, it does all this stuff. And the person's harnessed so they don't fall, but this piece of machinery is not cheap. If you're working physical therapy, this piece of machinery is $1 million treadmill. I don't know many physical therapist clinics or even hospitals that can readily buy $1 million piece of equipment. Okay, so that's really hard to do. What about coaching? Well, there should be some variability inherent in the system of a pitcher, but we have to work with what we have. If we're working with young pitchers, we have to be able to teach them the basics of it. But even when you look at some of the best pitchers, is they're able to change up their pitch very quickly. Some of the best pitchers in the world, one of the best ones before he went to Texas and worked with a whole bunch of cheaters at the Houston Astros and started stealing signs, and they became essentially cheaters, was Justin Verlander. He was the Detroit Tigers pitcher for most of his career. He was probably the best pitcher since Nolan Ryan, but he had a very, very good ability that he could change his pitch. So if he wound up and he was starting his pitch for a fastball, he was very good that he could switch not only how he held the ball, but the motion of his body to switch from a fastball to a curveball or a changeup during his actual pitch itself. That made him very hard to hit, because even if you're a batter and you know what his rhythm is like for how he pitches, or even, if you're on the Astros and you're cheating by stealing signs, even though you wouldn't be going against Verlander because he plays for the Astros now, but even if you have cheaters on your team that are stealing signs, all of a sudden that becomes very hard because you never quite know, and really you only have a split second to even swing at a baseball anyways. Often you'll hear batters say, like, they don't even look at the ball if they decide whether they're going to swing or not. They look at the pitcher to decide if they're going to swing or not. Because if you're waiting to see how the ball is going to behave to swing, you'll never, ever catch it. You only have a split second to actually decide whether to swing or not. So, can overly consistent behavior be bad for you? This is a big new area of research, especially in balance. One of the things we do in our Veer lab is we're a big balance and gait lab. We look at variability all the time. We look at it, if somebody's had a concussion, do they move more robotically? Is there too much variability? Is there just enough variability in their walk and their balance? What about overuse injuries? The injury doesn't really occur because you are performing the same motion per se, but it's because you are doing this almost identical motion repeatedly. And that one can be just a little bit different, so it's constantly stressing a structure. We can look at runners with patellofemoral pain. This is usually where we see the vastus medialis muscle of your quadriceps pulls a little bit harder than the vastus lateralis on the lateral side of your quadriceps. So it causes poor patella tracking within your femur. So over time, that starts to wear out the cartilage and cause damage to the bones. When we look at pitchers, we know, if you've ever looked at the shoulder, you have your rotator cuff muscles. One of them is the supraspinatus. It runs just under the acromioclavicular joint. When you do those overhead pitching, or anytime you bring your hand over your head, we see a small dip in that joint, and it places pressure on the supraspinatus muscle. And if we consistently overdo that, that's where we start seeing rotator cuff tears. Okay? When you hear of a rotator cuff tear, I would almost put a safe bet that it's going to be the supraspinatus muscle of the rotator cuff complex. It's usually a safe bet that it's going to be the supraspinatus muscle. Runners with injury had less variability in their lower extremities than non-injured runners. So when we look at that, it's constantly changing, so it's not placing the same stress on the same joint considerably all the time. So it isn't always the amount of variability, but sometimes the structure of variability that's important. So when we look at this, we have two subjects. We're looking at their heart rate. Okay? We have a young person here and an older person here. Let's look at kind of the structure of this movement. We see that if we're looking at the standard deviation, they're not too terrible. The young person has a standard deviation of 3.9. The old subject has a standard deviation of 3.8. So they're not that different. If we look at the entropy, however, we see that the entropy of the young subject is double that of the older subject. And we see that in the older subject, it's changing, but it's changing much less, and the magnitude of that change, the up and down, is higher. Versus when we see that the younger subject, the magnitude is a little bit less, but when we look at it, it's crunched together, okay? It's constantly changing. It's much more crunched together, but the magnitude of change isn't as different. So this is where we're looking at kind of the amount of variability or structure or quality of that variability. Okay, so this is from this is a really cool paper. I'll use a different color. This was a really cool paper that when you have time to read it, it was actually really well done, from Lipschitz and Goldberger in 1992, which may have been written before some of you have been born. But the amount of variability equals no difference between the young and old subjects. However, the structure of the variability and the analysis of it provide more information about the adaptability. This brings in what we consider to be the loss of complexity hypothesis. When we start looking at injury, or we're looking at pathology as far as diseases, when we start looking at stroke, we start to notice that these signals, either stride to stride intervals, heart rate, breathing rates, finger tapping, any sort of voluntary or involuntary human response, we start to see that maybe the complexity of these signals become less complex when we're looking at an injured or otherwise impaired system. So we can see this further. We're looking at the stride time of somebody that's prone to falls and somebody that's not prone to falls. Okay, this person's prone, this person's not. We're looking at the quality of these signals. This one right here has much more complexity than the faller. Once again, is the faller, we're seeing consistent changes, but first of all, the magnitude on the y-axis here are much larger and they're more spread out. It's almost like this is getting closer to kind of a normal sine wave versus this one where it's kind of a little bit all over the place. Okay? We see the same time if we're looking at somebody that's had an ACL injury in their knee. They learn compensatory mechanics of walking. So they start having this kind of normal sine wave for somebody that's not. So we see more complexity on the left side here. So how can this information be used to help? First, we have to get a good understanding of the underlying dynamics inherent within each population. This is a big ask. We have to look at infants, kids, adults, kids, and infants in different clinical populations. So even if we're looking at gait and postural dysfunction, let's say we know, let's say we somehow built a computer that is the smartest computer in the world, okay? Usually when you hear about artificial intelligence and all this stuff, it's a shorthand for a computer that can do a lot of statistics very quickly. So let's say we built that computer and it was able to determine the optimal amount of complexity in gait and posture. What about that for somebody that had an ACL injury, or in healthy participants, we're looking at age? What about traumatic brain injuries? These are concussions. Can we look at those? What about cerebral palsy? What about people that have an amputation? Now they're working with a non-biological leg. What about people that have had a stroke? What about Parkinson's? What about multiple sclerosis? Or even Huntington's disease? Huntington's disease is a terrible disease in which the nervous system basically rapidly dies and people cannot control basic functioning of their body. And we see an increased loss of complexity in there. So this subject, once again, if you guys are thinking of going into the clinical world or you're thinking of going into possibly going to grad school and you're thinking like, what am I going to study? There is so much research that you could do with this that you will never, ever, ever run out of ideas. There's so many ideas that have yet to be even thought of in this type of research. So after you do that, second, we need to develop novel ways to change their movement variability. Can we think of different training regimens? Can we think of other devices that can use this? Once again, that treadmill, it works very well. It's $1 million treadmill. Is there any way to do this? One of the ways we measure it, we have the AppWalker app that we developed in the Veer Lab. And we got it through the Department of Defense, got funding through the Department of Defense. And we developed the AppWalker app, which is an application used for Android smartphones. We place it on the side of their leg and have them step in place with their eyes open, eyes closed, while they're shaking their head. And we measure the variability of their knee flexion, their thigh flexion, the cadence or rate of them stepping. We measure all these different things. So that brings us to kind of, this is going to be the last slide, but can we use variability to design better robots? Boston Dynamics is a kind of really amazing technology firm. They build robots. They build robots for the military. They build robots for industrial purposes. But one of their kind of crowning achievements was Atlas. It's a bipedal robot that is supposed to have a very strong computer on it, and it can respond to it can respond to its environment. So let's take a look at this and notice that even with some of the very, very best programmers and like that, does it still look like it's working like a human? Look, it's opening up a robot. Everyone's freaked out about that it's opening up a door. But they have it walking up and down a snowy hill. It has to use variability so that it can compensate for this environment. By the way, this video is even better with sound because there's some funny comments. It can pick up boxes. It can do all sorts of stuff. Boston Dynamics releases these videos every so often. One of their common ways they release these videos is they beat up on these robots. They're kind of mean to these robots, but they're looking at how do these robots respond to a changing environment. They push it around, they take away its box, it has to move to its box. These engineers, they build some really cool stuff, but they're kind of mean to these robots, which I don't know if these robots ever get more advanced. They might have to stop being mean to them. There's also, some really good parody videos of this. But are we seeing that we can start studying this? Like, just push down the poor robot. But once again, this is a really cool subject. I highly suggest you guys do some reading on this when you guys have time. This will be on the final exam, but it won't be a large part of it. Like I said, understanding what variability is and the definition of it, what is homeostasis, what is variability, how do we measure it, stuff like that, you should be fine. So I hope this was an interesting lecture, a little bit different from the other ones. And if you have any questions, please let me know. Goodbye.